Those of you who've been at the conference before know we have a bit of a thing with Albert. Were you waving to me? No? Oh, all right. He's probably the most famous person on the planet, and he's certainly the archetypal image of the scientist that Adam Bly was talking about yesterday. At a previous conference, we've heard the rather bizarre story of Einstein's brain. Do any of you remember it? After Einstein died, this coroner in Princeton, New Jersey, quite without permission, hijacked Einstein's brain. He did the autopsy and stole the brain, and this brain sort of sloshed around in a plastic bucket for years in the trunk of this guy's car. I'm not making this up. Eventually, he sort of got tired of pretending that he was going to do something scientific with it, that he decided to give it to someone else, and that someone else was Sandra Whittleson, a professor at McMaster University. And another of our speakers, Carolyn Abraham, who didn't speak yesterday, for good reason, she's just had a baby, chronicled in a book this bizarre scene as this kind of car drives up to the border and the guard comes over and says, "Have you got anything to declare?" And the guy says, "Well, nothing except I have this brain in the back." And the guy says, "Sure, whose is it?" "Albert Einstein's." "Oh, yeah." Waves him right through. And Sandra came to tell us why it was that he was Albert Einstein and we are not. Apparently, that part of the brain that deals with spatial calculation and so on is literally and physically larger than the average or mean brain that the rest of us possess. So that's how I came to invite Michael Shama to be with us, because he is the fellow who has just curated an enormously successful Einstein exhibition at the American Museum of Natural History. He's also an astronomer, and his specialty, or one of his specialties, is the collisions between stars. And I don't know if you know this, but we're doomed. No, I'm not kidding you. The Andromeda Galaxy, which is the closest galaxy to our own, is on a collision course with the Milky Way. And in only 4.5 billion years, we're...
Well, thank you very much. We've heard lots about doom and gloom, and yes, astrophysicists can come up with gloom and doom scenarios that'll make anything that any of these guys are worried about, anthrax or nuclear weapons or chemical or biological weapons, make it all seem pale. That's right. We've got it all nailed down pat. Let's go to the PowerPoint presentation right away, please, because I actually want to cover two ideas for you. The first one doesn't have directly much to do with Einstein, perhaps, but I think that you will see a connection. This is really what I spend my time, or a lot of my time on these days, and that's the search for planets around other stars. We know of 8 planets in our own solar system. Many astrophysicists, myself included, no longer include Pluto in the pantheon of the planets. We think it's the largest and most regal of the objects in the outer part of the solar system, the comets. But the search for planets other than those orbiting our sun is going to be very intimately tied in with the search for life off the surface of the Earth. Now, it's certainly true that going to Mars, going to Europa are going to be critically important in answering the question, is there life elsewhere in the universe? The other way, of course, is simply to listen. Broadcasting doesn't do you much good because it takes centuries or millennia or millions of years for the signal to get out there and a long time for the signal to get back. But maybe somebody is broadcasting the Encyclopedia Galactica and we haven't yet cottoned onto it. The SETI project, the Search for Extraterrestrial Intelligence, is trying very hard, so far without success. So we're trying something else, and that is actually to directly capture images of extrasolar planets. That has not yet been done. Now, if we did capture a planet which had an oxygen atmosphere, and the Earth does, we would hope to see bands of ozone in the spectrum, water vapor. We would see carbon dioxide also, but we see carbon dioxide on Mars, which may or may not have life, and Venus, which almost certainly doesn't. So there are some other, if you will, thumbprints or DNA in the spectrum of extrasolar planets that may tell us, or at least hint to us, that there is life elsewhere in the universe. And that's something that we're trying very hard to do, and I'm trying very hard to move forward and aren't succeeding. So I wonder if you can move me to the next slide, please. Thanks. And yes, it is 1491 in terms of galactic astronomy. Queen Isabella has signed on board. We're building the ships. In fact, astrophysicists have found about 100 exoplanets so far. Not a single one of those planets has yet been imaged. How have we found those planets? Well, those planets rattle around. They move in orbit around their host stars, cause the stars to move back and forth. We take spectra of the stars. We see the spectral lines shift back and forth, the Doppler shift. That's how we know that the planets are there. But again, not a single picture exists. And I'm going to ask you to move forward, please. Next slide. Can we have? He thinks he has it. Okay. The key point here is, next one, please, is that not a single one has been imaged, and I think that that's going to be the next big challenge and the next big thing that you're going to see coming out of astrophysics. Next, please. We plan to go to Haleakala on the summit of Maui. There is a fantastic telescope there run by the US Air Force, and basically they look at satellites passing overhead, and they're able to get rid of the twinkling of stars. They're able to flatten out images that are wrinkled and crinkled by the atmosphere of the Earth. Next, please. This is the kind of picture that they can take. This was Columbia, in fact, on its last mission. The level of resolution is remarkable. We can actually peer up through the atmosphere and get rid of all of the turbulence. But that's not enough. It turns out that there's a second requirement. Next slide, please. And that is to block out the light of a star. If we want to see a planet next to a star, directly image a planet next to a star, it's rather akin to taking a picture of a firefly next to a 10 million watt searchlight pointed in your face. So you've got to suppress the light of the searchlight, and the first attempt at doing this was done by the astronomer Leo in the 1920s, and he succeeded in picking out the corona, the atmosphere around the sun, basically by putting a disk of aluminum in front of the image of the sun, some very clever optics behind it, and he was able to suppress the light of the sun by about a factor of 10,000, make it 10,000 times fainter, so that the faint corona could be seen. We need to do 1,000 times better than Leo. We need to suppress the light of a star by a factor of 10 million in order to be able to see a planet next to a star. And that's a major technological challenge. This is the device we're building at the American Museum of Natural History. It's called a Coronagraph, not aimed at looking at the corona of the sun, but aimed at picking out planets around nearby stars. And the next image is something like what we would hope to see. Now, this is actually 100,000 to 1 success. A picture taken with the Hubble Space Telescope shows a very, very faint nearby star and a brown dwarf, a failed star next to it. This is not quite a planet. This is an object that's, about 40 or 50 times the mass of Jupiter. And it doesn't quite have enough self-gravity to turn on nuclear reactions in its core. As a result, it's a failed star, more than a planet, less than a star. But we know that there have to be, we've already observed them because of their gravitational rattling of stars, planets around nearby stars. So can we observe them directly? And the answer is unquestionably yes. Next one, please. Well, the first planets we're going to be able to see around nearby stars are the Jovian planets, the analogs of something like Jupiter in our own solar system, or Saturn or Neptune. But if we're lucky, and if we're good, we're actually going to pick out, I think, a new class of planets. Because there are two flavors of planets in our solar system: Jupiter, Saturn, Uranus, Neptune. And then there's the little teeny guys: Earth, Venus, Mercury, Mars. Why isn't there something in between? Why is there this huge gap of about a factor of 30 or 40 in mass? Why isn't there an object 3 or 4 or 10 times the mass of the Earth in our solar system? It may just be dumb luck or bad luck, perhaps good luck for us, because that could rattle around the orbit of the Earth in very unfavorable ways. But there may well be such objects orbiting other stars. And in fact, if we're really good, sometime around 2015, we may not only detect the presence of an Earth, but by 2020 or 2025, hopefully start getting really high-resolution images of Earths using something that NASA is calling the Terrestrial Planet Finder, the next really major project in ultra-high-resolution astrophysics from space. Well, let me get on to what Moses really wanted me to talk about, which is Albert. Albert is on until the 27th of July at the American Museum of Natural History. After that, the exhibition will continue on to Chicago, Boston, Los Angeles, before all of the original papers return to Jerusalem in 2005 for the centenary of Albert Einstein's Annus Mirabilis. In 1905, he wrote 4 papers which revolutionized the world. They changed our civilization in ways that we are still feeling. This is the picture that many people have of Einstein. You think you know where he's going next, though he may still surprise you. Next, please. We did a survey before we ran the exhibition. What did people know about Einstein? What did they think about Einstein? What impressions did they have of him? And this is the collective picture. The father of the atomic bomb. There's both the mushroom cloud and the bushy hair, wise old eyes. And that was about it. Many people connect E equals mc squared with him also. And it's astonishing how much little else is known about him by the public. Well, they were correct about one thing. And there's a wonderful letter from Ann Cosin, who lived on Central Park West. I think you ought to have your hair cut, sir. You can look better. Cordially yours, Ann Cosin. Really a neighbor. There was an adult involved in this. You know, you can do some conservation here, and you can see that the word ought, O-U-G-H-T, was corrected by her mother. Next, please. How famous was he? Well, this is a letter from Indonesia. Mr. Einstein, the atomic scientist USA. It was delivered in 3 days. Here's the changing view of Albert Einstein. 1950, when he was still alive, he is pictured as the father of the atomic bomb on this cover of Time magazine. 1979, the centennial year of his birth. You can see galaxies and stars popping out of his head. He's become the father of cosmology, so he's no longer associated here with the atomic bomb, no longer seen as the father of the atomic bomb, but rather the father of modern cosmology. And here you have Saint Einstein. He has been transformed. He has been beatified. Next, please. And that's something we wanted to try to change, or at least bring down to reality. So our exhibition, which contains almost nothing but original documents, many in his own handwriting, talks about physics and relativity and much more. And in the next 5 minutes or so, I'm going to explain both special and general relativity to you. You think I'm kidding? I'm going to tell you how he changed our world. We have letters to and from his wives, mistresses. There were many. Women loved him. He loved women. His enormous courage during the period of McCarthyism, something I hadn't really appreciated till I did this exhibition. He was a lifelong pacifist who is intimately associated with the production of the atomic bomb. When he died, even though he was a loyal American who actually warned President Roosevelt about the coming of the atomic bomb, he had accumulated an 1,800-page-long FBI file. You can visit it at www.fbi.gov. It's on the web. He advocated a unified world government and peace between and coexistence between Israelis and Arabs, and letters that he wrote. One in particular in 1929 could have been written yesterday. It's as applicable today as it was then. Well, there's this urban myth that he was a mediocre student. We have his report card on display to give lie to that. 6 is the highest grade. Geometry is 6. Descriptive geometry is 6. Physics is 6. History is 6, and algebra is 6. Really not bad for someone who was supposed to have been a mediocre student. He wasn't. He was always an excellent student, though he spoke late. And I think that's where some of the myth may have come from. In fact, there's the story that until he was 3 and a half, he didn't say anything. And one day, his mother gave him a glass of milk that was too hot. He burned his tongue, and he turned to her, and he said angrily, "Mother, why did you do that? The milk is much too hot." She looked at him, and she said, "Albert, you've never said anything until now." And his response was, "Until now, everything was perfect, thank you very much." We have him pictured here with his first wife, Mileva, their daughter, Lieserl. And in fact, Lieserl vanished from history. We didn't know that she existed until 1986, 87, when her existence was revealed in letters that were finally made public many years after his death. Lieserl almost certainly had scarlet fever and was given up for adoption. She was born out of wedlock to Albert and Mileva. They married a couple of years later. They did have 2 other children, and there are many descendants who live in the Los Angeles area today. This is the beginnings of a love letter to Mileva. This is before they were married, and he starts it off with his very romantic, "My little kitten," and I would hope that the heartbeat of every woman in the audience beats a little faster as she sees this. Let's see the continuation. I have just read the most marvelous paper by Leonard on the generation of cathode-rays Beltrabad, but now, what a romantic fool, that Albert. I do point out that Mileva was studying for her PhD in physics also, so she may have found the second part even sexier than the "My Little Kitten." Well, a few of the great applications of his work. He discovered Brownian motion. It looks like my molecules are not jiggling. These are little bits of fat in a drop of milk. And they jiggle incessantly and they wander all over the drop of milk. And Albert Einstein explained this. You might say, well, so what? This was able to lead him to demonstrate that molecules really exist for the first time. Not only that, but the size and the mass of a molecule. And this led very quickly to an understanding of crystallography, X-ray crystallography, which was used by Rosalind Franklin in the early 1950s to take images of frozen DNA, which in fact led to the genomics revolution of today. That doesn't mean that Einstein is the father of genomics, but he laid the theoretical basis by demonstrating that molecules exist and what their sizes and properties are like. In the same year, in 1905, he also wrote a paper on the photoelectric effect, how electrons are ejected from metal when they're irradiated, that romantic paragraph to Mileva. And in fact, that led rapidly to the development of vacuum tubes, and those vacuum tubes led to a communications revolution almost as revolutionary as the one that we're having today. And for that, he was awarded the Nobel Prize because the Nobel Committee was afraid to award him the Nobel Prize for relativity. Relativity was his great invention of 1905, special relativity, and that invention terrified physicists because it was so radical and so different. And then finally, as an afterthought, in fact, he noted afterwards that he thought God was playing a joke on him, E equals mc squared. And E equals mc squared is the basis for nuclear weapons, nuclear power plants, and our understanding of why the stars shine and why there's carbon in our muscle and calcium in our bones. All of that in the space of 1 year. And he had a day job. He was a patent clerk, so he did all of this at night, all of this in the evening. And in fact, there are the jiggling molecules. If you look at a drop of milk under a microscope, that's what you see. And it's because the little droplets of milk are being hit by molecules of water that are moving around. And he could deduce the size of a molecule, the mass of a molecule, basically on the basis of what we now call statistical mechanics. Again, the Nobel Prize, which we have on exhibition. Next one, please. And then he invented something called a light clock. And the light clock is this beautiful little device where you bounce a beam of light back and forth between 2 mirrors. It was known since the late 1880s, but not believed by physicists. It was counter to their gut instincts that the speed of light is a constant in a vacuum. All observers see the speed of light as being the same, whether you as the observer are standing still or moving relative to the source of the light. Well, what does this mean? It means that if instead of taking a stationary light clock, you take a moving light clock, you're going to see that moving light clock tick at a different rate. If you all sit still here and I go outside and run around the auditorium and come back and I compare my clock with yours, if our atomic clocks, which had been synchronized to a trillionth of a trillionth of a trillionth of a second when I left, will no longer be synchronized because I've moved through space in a different way than you have. Moving clocks run slowly. Let's see the next image, please. There's a moving light clock. Now, I told you that the speed of light is a constant for all observers. If the speed of light as it moves along this diagonal path is the same, but the distance is greater because the light now has to move along the hypotenuse instead of along the vertical O, then you have to go further in the same length of time. If you have to go further in the same length of time, it takes longer. And so the clock ticks less frequently. And that's why moving clocks run slowly. That's the way the universe is built. And it's built that way because the speed of light is a constant. Einstein also explained how gravity works with the simple analogy. He said the sun at the center of our solar system is like a cannonball sitting in the middle of a trampoline. And the trampoline surface is warped. And as we roll a marble across the surface of the trampoline, the marble will follow a curved path, not because of a magic invisible action at a distance from the cannonball, but simply because the surface on which it's moving is curved. The reason the Earth moves around the sun, the reason there is gravity, is because the sun is curving space-time around itself. And the Earth then follows a circular or elliptical path around the sun because it's trying to follow the shortest distance between 2 points on a curved surface, which in the case of the Earth is a closed ellipse. There's Einstein's dramatic prediction that light should be bent as it passes by the limb of the sun. And an eclipse expedition in 1919, which took pictures of stars, you can barely see them here, near the sun during a total eclipse of the sun. Those pictures were compared with images of the sun, of the same piece of the sky when the sun was not there, and indeed the stars were shown to have been deflected. And in 1919, Einstein became, as one of my colleagues has described it, as famous as Madonna, George Bush plus Tiger Woods rolled into one. He also predicted lensing of light, lensing images, and in 1996, this beautiful image taken by the Hubble Space Telescope shows a cluster of galaxies with more distant galaxies in the background warped and bent. Einstein, the man, is also featured in our exhibition. He was an extraordinary human being. His one sport, his relaxation, was sailing. There's a double entendre here for physicists. It is, in fact, the sport which demands the least energy. More important was 1939, the famous letter to Roosevelt in our exhibition, where he says this new phenomenon of fission could also lead to the construction of bombs, and it's conceivable, though much less certain, that extremely powerful bombs of a new type might thus be constructed. E equals mc squared yields these terrible weapons, but it also explains where the power of the sun comes from, fusion of matter. And as we're going to hear very shortly, it's a prodigious source of these wonderful particles called neutrinos, a great triumph for nuclear astrophysics, which has been done here in Canada. To conclude, he was offered the presidency of the State of Israel in 1952, wisely declined. And as I said, had this huge file garnered by the FBI because he associated with known subversives like Charlie Chaplin. In 1953, he refused to testify, or would have refused to testify had he been called before one of the Senate subcommittees, and advised people to do the same. His obituary, done by Herblock, really summed up in a pictorial form: Albert Einstein lived here. We have an ongoing quest to try to understand the nature of the universe. The search for a unified theory of physics goes on, something he taught us. And a final quote from him in the final slide: "I have no special talents, I'm only passionately curious," something I think very appropriate for this forum. Thanks very much. pleasure.